Okay, so we have discussed this RNN in the last class, and I have given you the example also. So how it is working, and what are the steps that model needs to follow for getting the output while we have given the sequential data. Now let us see uh, what is the uh, what is the problem. Again, whatever you have seen, it will give you, like, your RNN will give you better performance. It will give you good performance, promising results. Those things are there, but there is some problem here, and let us just see that problem, where the problem is involved, and can we solve that problem. Okay, so if you just see this part, when you are coming to this part, so what we are doing, we are adding the vector. We are giving the vector for each character. Okay, and then you are applying the formula, and you know the formula. The formula is like W WXH WXH. Now it's fine. So what I was saying that uh, in this case everything is fine, but one problem is there, and that problem is due to this. Okay, so when you are finding the state, suppose you are going to find the state h1. So what you are doing, you are applying 10h, and then you have wxh and into x1 plus whh into your h0 and plus bias. Okay. Now, if I just see x1, what is x1? Your x1 is one hot encoding vector. So in this case, like, let us consider the first case. So your x1 is 1000, this vector, and this vector is getting multiplied with the wxh matrix, and that matrix is of dimension 3 by 4. Okay, now what is happening here? For getting the, because this will be multiplied with this matrix and it will give you the output vector. Now if you just carefully see here, and what is happening in this multiplication, only this part is being involved, because for other parts we have 0 0, so it's getting multiplied with the 0. So when we do the multiplication, so either you can do row by row, at a time you take one row and multiply with this particular column, or you can take this as a the the summation of, like, just multiply this value with the first column, multiply this value with the second column, multiply this value with the third column, multiply this value with the fourth, and add all those things. So you can also do column by column. So either you can go row wise multiplication, or you can go column wise. Okay, in, like, whatever step you are following, what is happening, only this first column is getting involved for getting this output, because others are getting 0. Why? Because it's getting multiplied with a 0. So if you just see in the output, we have, if you just multiply this thing, so in the output you will be getting just this value, W11, W21, W31, W41, only these 4 things. So this is the problem. Why this is problem? Because for getting the output, every value of this W matrix is not getting involved, and that's the problem. Because whenever I'm going to decide something, everyone should participate from here. It's just like if I'm going to take the decision here, about this class, then every participants whoever are here, they should participate. But if they are participating and I'm not considering them, then that is wrong. So in this case, these guys are, they are going to participate. They are participating. But since we have, like, I am biased. So this is me. So I'm biased. I'm biased towards this, or I'm biased towards only first column. So for other columns, I'm giving value 0, 0, 0. So while doing the multiplication or while taking the decision, I'm biased towards some of the students, and I'll just give weightage to them only. And for remaining students, I'll just give weightage 0. That is problem, because whenever you are going to take one big decision, you should give attention to everyone. But this is not happening in this case. So everyone is not getting attention. Like every value of the W matrix is not getting attention. Why? Because of your input. Because your input is like sparse vector. So in the input, you are having most of the values 0. And that's the problem. Okay. So if you go with this, it's fine. You can get the model. But the thing is, every value of the W is not participating for getting every output or getting every state. Okay. Okay, so this is the problem now. How to solve it? How to make everyone to participate? So for that, what you need to do? You have to somehow make this vector dense. It is sparse, and due to that sparsity, you are getting the issue. Now, how should I make this vector dense? Dense means like most of the values should be non-zero. Okay, so that's the goal. But here the problem is like most of the values are 0. So how to make it like how to make most of the values non-zero? So for this, what is being done? We include one layer that is called embedding layer. So the goal of the embedding layer is to take the sparse vector where we have most of the zeros and transform it into dense vector where most of the values would be non-zero. Okay, so we add one extra layer, and that will convert this representation, one hot representation, into dense vector. And if you just see the dense vector, we'll be having most of the values non-zero. Okay, so every vector, every sparse vector should be converted into dense vector. And for this, again, we have one separate layer. And in that layer, we could be having, it could be having any type of function which will do it, which will transform sparse vector into dense vector. And it should be having also the reverse part. So like even you are going from sparse to dense, then you should be having path to go from dense to sparse, because at the end we also need a sparse. Okay. So for this computation, like for getting the state, we need a dense vector so that everything will be smooth. And that's why we are adding this embedding layer here. But again, if we are going back, because sometimes we also need go from sparse to dense to sparse. So we also need that part. So actually, what generally is being done in this layer, we will be having some type of encoder decoder layer. Sometimes people also use transformer here for getting this embedding. Okay, so it will be having like encoder and decoder type of layer. Okay, so encoder layer, the goal of the encoder layer would be encoder network would be to encode the features. Okay, so whatever information I have, make it dense. That's the goal of this part. And then the goal of this second part is to take that dense vector and again make the sparse, same as what we have at the starting, like as an input. Okay, so this actually we train this network in this way. Okay, so again, this is sort of encoder decoder type of network, and we train it so that it will like it will learn this same to same, like given whatever input I'm giving, learn the same as a output, but the game is in between here. So here the goal is to get the dense vector, and from dense vector second part will take, and then it will give you the sparse vector. And again you'll find the loss, like how good it is doing, because this is, again, this is being also going, you have to train it, but sometimes you will be getting, because most of the already people have done this thing and you can get the train model. But if it is not there, then you have to train this part also. Okay, so this part will do it, and for this, for the training purpose, again it will take whatever output it's getting, it will match with the input, and then it try to minimize that distance. Okay, so at the end what happened now, when we started to give you the good output, then what we generally do, we take the encoder part for this. So encoder part will be used as a for the embedding layer. So encoder part will take this sparse vector, and it will give you the dense vector. And then maybe if you also need this decoder part, because at the end, suppose you want to convert your dense vector into a sparse vector, then you take it and give this dense, whatever dense vector you got, give it to this part and get the output. And this is just one mechanism, just but you could also use some already fixed function. So it depends on you, like what you want to use here. But the goal is to make the vector dense. That's the goal. Now remaining things will be same only. So just now these are like having non-zero values, and then give to the, again apply the same function, all those things whatever we have seen before. So this will be getting multiplied with the WXH, and this again will be having a past hidden state that will multiply with WHH. Add sum these two term, then add the bias and apply the 10H, you will get this thing. So now other things are same only, just we have added one extra layer here, which is giving you the dense vector. And you have seen like what is the uses of dense vector, because you want everyone from here should participate in getting the output. Okay, now let's go for the back propagation. Now back propagation is slightly tricky in this part. So in the case of CNN, or fully connected layer network, what we were doing, we had the network here, and we were giving the input here, and getting the output here, finding the loss, and then going back, like doing the back propagation, like finding the gradients by applying chain rules, and then updating the W. Now in this case, how should we proceed for this back propagation? How should we do this back propagation? Now if we just see, in the case of RNN, we have the concept of states, and we are generating multiple states, depends on the number of words that we want to process. Suppose these are the words, these are the inputs, and every input, with the help of every input, you can generate one state. So one is one input and the past state, combining these two things will give you the current state, and then using current state you can get the output. In this manner you can generate a lot of states, and for every state you can get output also. And now you have to find how good your output is. So this is one prediction, second prediction, third prediction, fourth, and so on. And you have the actual ground truth also, actual value also. You compare with every output here, compare with the target output at every like for every output, and then find the loss, and then do the back propagation. Now go back. So when you are going back, you have to go via all the states from every state, because your state is also variable. Your state is also variable because state is getting changed, because it depends on your input and the fill-in state, and you are applying the fully connected layer there. Okay, so what you have to do, you have to go back, and with like through every state, you go through the states, like you'll generating all the states. Finally, you will be reaching somewhere, and then you also have got loss at every at the output of every state, from the output of every state, and then you just summed all the loss, just aggregated all the loss, and then you will go back. Okay, now if you are going back, so again you have to traverse through the states, and you know that at every state your W is like W's are same, because W's are shared across the state. So you have to just update the W. If you are going to update the W just at the end, that's also fine, because you are just going to update the C only, like you are going to update the same W every time. So why not we should update it at the end? So what we'll do, we'll just process, we'll go back through every state, like finding the gradients, and then at the end I'll update the W. So I'll update WXH, WHH, WHY. These are the W's that you have to update, so that next time it will give you the better result. Now the thing is, it's not easy process. Why? Because the one thing is that it's time consuming process. So suppose I have given you this book, Corman book, that is like algorithm book. It's like a huge number of pages are there in that book. A lot of sentences are there in that book. And suppose I'm giving you that book, and then saying you like, hey, you decide like how good this book is. So what you are going to do? You are going to decide, or maybe just change the problem. It's not like how good this book is. Instead, suppose I'm giving you that book, and then I'm saying you, hey, you generate the you train the model which can generate that book. Okay, that's the goal. Okay, generate the book means it can generate all those sentences. Okay. Now, if you're going to train this RNN on Corman book, now Corman book is having huge amount of words, and you're considering one word as a one input. So if you have huge amount of words, maybe just processing the Corman book may take 2 days, 1 day, or maybe more than that. If that is happening, you will be not able to train it in a proper manner, because you are just waiting for 2 days. You are just waiting for 1 day. And once you process every input, then at the end you are aggregating all the loss, and then you are going back. Now it's very time consuming process. And suppose if in between something wrong happened, then again you have to do it from the starting, because you have not updated the W. You are just waiting for processing every input, and then you'll be going for, like, you'll be aggregating all the losses, and then you'll be going back to find the gradient, and then finally you'll be updating the W. So if you are going in that way, then there is problem here, because very, very time consuming process. And even what you have to do, if you are processing every state, you also have to store the information of the states. And if you have huge trillions of states, millions of states, then what will happen? You have to somewhere you have to store these all the state information. Again, the challenge would be space. Wait, how to store this much information? So we have two type of problems here. One is space and one is time. Both the problems are here in this case. If you are processing every input and then you are finding the loss and then you are going back for doing this back propagation, then what should I do? Because if I process the entire sequence, then there is problem. Then what should be the alternate way? So that alternate way is go with truncated back propagation through time. So instead of taking entire sequences, now what I'll do, I'll take only some part of this. So this is like truncated back propagation through time, because this is happening in the time. These are like sequential information. Okay. So what I'll do, I'll just take few words, like selected numbers. Just I'll divide into, like maybe I'll fix n number of words, and at a time I'll just take the n number of words. Okay. So these are the words, and I'll process, like every word is getting processed, getting states, getting output from every state, and then I'll aggregate the loss, and then I'll do the back propagation. So this loss is being calculated, and then go back and find the gradient, and then with the help of gradient change the WXH, WHH, and WHY, because these are the three things that we need to update, and we'll do it. Okay. Now suppose this part is done, then I'll go for the next chunk of words. Okay. So this is the first part. Suppose this, we are just going to process the book of Corman, that Corman book. And so what we are doing, we are processing n number of words at a time of that book, and then going forward. Okay. So every n words will be processed, and then we'll find the gradient, we'll update the W, and again we'll go for the next n number of words. Okay. So you got this WXH. Now you have got WXH, WHH, and WHY. These are like updated, because it has been updated. It have been these all the things have been updated by your back propagation here, your stochastic gradient descent. So you are applying now for first n number of words, you got the gradients, you applied the this gradient descent type of a method to update these W's. And now the next chunk will be having all the updated W. And again it will start from here. So it will take the previous state from here, the final state of the last chunk, and then it will again, it is having input, and then it will generate the state, and this new state is getting generated by the updated, fully connected updated value of the W matrix. And then again it will go up to like n more like for these n words, and then again it will find the loss at every point, and then finally this is the aggregated loss, and then we'll go back. Okay. And in this way you will be doing for every chunk. Okay. And finally, once you reach at the end, now this is one iteration, because you have processed every word of the book. So now once you have completed this, now that is one iteration, and again you will go in a similar manner for the second iteration or the second epoch. Okay, so in this way, like this process will be simpler. It will take less space, and time complexity would be also lesser. Why? Because your W is updating after every processing, like after processing every n inputs. That's the good thing, and people generally follow this truncated backpropagation, and this is like common method for backpropagation when you are going to use RNN. So let's see some of the examples where people have done it. So this is the paper which came in 2015 by Karpathy. So what he has done, uh, like they have trained this RNN for the sonnets book, which is by William Shakespeare. So like this RNN has been trained for generating this the books, generating the paragraph or sentences of this book. Okay, so this RNN has been trained on this the sonnet book, and let's see how it is happening. So at the starting, like when you are going to train this model, so at the starting, since it is knowing nothing, because it's like get your W's are just like random values there. So at the starting, it will generate any random stuff. So you can see like in maybe for first chunk or maybe for few chunks, you might be getting this type of thing. Like there's no meaning of this. You are getting just alphabets are coming, but there is no meaningful word or sentences that you are getting here. Just then again you train more. Now if you see like it is started to give some meaningful words, but still there is no meaning of the sentences. You can see like here I feel on. These are the words. Those are getting generated by that model. Even if you train more, now you can see now words are like at least we are getting meaningful words. You can see here most of the words are like having some meaning, but still we are not getting proper sentence. Now if you train more, now you can see like now it started to give you the sentences also. Why do what that day, replied Natasha, and wishing to himself the fact that a princess. So it's like the things are these all the things are being generated by your RNN, and it's looking like coming from the sonnet books. So it's generating the similar type of sentences which we have in that sonnet books. So the sonnet book. So it's like you're training the model to learn that book. Like how if I say you like generate it, then this model should generate it, but it should not be same as that book. It should give similar type of book with respect to this sonnet. So it will be having similar type of structure what we have in the sonnet book. Okay. So now you can see like this is being generated by the RNN. So you can see like in the similar structure, it's also taking different character. Then they are saying something. Every character is saying something. Then response. So these all the things are like being generated by your RNN, and the RNN which has been trained on the sonnet book. Yeah. Further, they have also trained this RNN for RNN on this algebraic geometry textbook, and where we have all the LaTeX file. So what they have done, they have just taken all those LaTeX sources, and in this, if you see, like we have a lot of chapters from introduction to commutative algebra, and then they have trained the RNN on this book, and let's see the result. So now your RNN has started to give you all the proof, lemma, all those things. Yeah, like I'm not saying that it will give you all the correct proof or all the correct lemma, but at least you are getting those things in a similar manner. So at least if you just see the structure wise looking very similar to the lemma or this proof what we have in the book, but correctness, that is like again question mark. So that again you have to check it whether that particular lemma or proof is correct or not. But at least it has learned this thing and it started to give you the structure. That's also the you can say in some ways also one type of we can say the magic that you're getting here. Okay, so just like us, it's also learning from the book, and after, like, once it is being trained, then it started to give you the proof, lemma, all those things. Okay. But correctness is, that's the question, so that you may check it. And you can see here all those things, structure, this image, some type of graphical structure, everything is coming from the model. Lemma, you can see lemma 0.03. These all the things are coming from the model. Further, they have trained it for the Linux operating system, and you know that Linux operating system is it is having C inside that, so that operating system has been built using C. So they have just given this the source code of the this Linux, and then they have trained it for using RNN, and then you can see, like, now your RNN can give you any type of C code. You can see static, void, these all the things are coming from RNN. So your RNN is generating this code. Even it's giving all those comments, everything, all header file, all those things. So everything is coming from the RNN. These are all the things, all the codes are generated by RNN. So what I'm trying to tell you, like, nowadays, you know that we have ChatGPT, you have all other LLM tools. They can also generate code. They can also generate different type of proofs, lemma, everything. Whatever you are going to ask, it will give you. But this is not new. It was already there even around 2015. So these all the things, whatever I'm discussing here, these all the things were there at like 2015 also. So this people already have done. Like, if you just see the paper, these all the papers are from 2015, even before that. So things were there. But again, nowadays, what happens that we have better model or better architecture, or or you can say like the faster model compared to this. So whenever I'm saying fast model, that means training would be fast. Testing wise, still we are facing issue even in the case of LLM and all those large language model, because those are having huge amount of parameters, and that's the issue. And that's why, like, you'll be not able to train that model on your system. You should be having proper GPU, then only you'll be able to train it. But these all the things were also there at that time in 2015, and that time also with limited amount of GPU, still people were able to train the RNN for solving these all type of problems. Okay, but again, now things are far better. We have tools. We have software which have been developed by some, or we can say, big company. So they are providing these all the things to us, and that's why nowadays it's easy to use it. That time, if you want to do something, you have to train it, then you test it, then you do it for your purpose. But nowadays, things are already available. Take it, use it. Even you don't need to understand the code and all these things. Just you have the software. You have all those softwares are available. Just use that. That's all. But you have to pay it. So if you are going to use ChatGPT, you have to pay it. Okay. So I was just, why I told here, why I put these all the things here, because you should it should not be looking like these all the things are just came. No, it was already there. This is just evaluation of that. That's all. Okay, so let's see one more example. It's image captioning. So I already have told that image captioning is like we have image and you have to describe the image. So whenever I say like whenever we are dealing with the image, we need CNN type of model also, because CNN will process it, because you know that on image CNN is most suitable layers. So we apply CNN over the image, and then we get the feature from the CNN, and that will be given to the RNN for the for the captioning task. Like your RNN will give you the captions, like description of the image. Now, how it is happening? So here, what will happen? We'll take convolutional neural network in the first part, which will be like pre-trained model. So, like maybe you can take any model here, and that model would be trained on some other data set, like image data set. So, purpose is to get the feature from this model, and then give that feature to the RNN for getting the description of the image. So, what we generally do, we this is the CNN model, and this model has been trained on ImageNet dataset. Now what we do, we just chop off the last layer, just remove the last few layers, like only last layer, because last layer is doing the classification, but we are not interested in the classification here. In this case, our job is to describe this image. Okay, but for this image we should be having features, because we cannot walk in the image space, because image is having a lot of noises also. So why not we consider the CNN model and take the best feature from that CNN model, considering this image, and then give that feature vector to the RNN for getting the description. Okay, so the same thing we are doing here. So this is the pre-trained model, and chop up the last layer, and just we are giving this. Suppose we have to describe this image, so giving this image to this model, and then finally we are getting the feature from this second last layer, that is like 4096 dimensional vector. So you can see here. Okay, and now we have to generate the text. So for generation the text, for generating the text, what we do, we have to start from somewhere. Okay, so there is a start token, starting, or you can say start word. Okay, so this is like fixed word. That means like we are saying, hey, now we have to start giving the description. Okay, so this start word is again having the this vector assigned to this, just like I discussed in the previous class, like every word should be converted into vector. So this start is having the vector x0, and then you will be going to process this x0, and with the help of x0, that is your input word, and you have the hidden state also, the last state. Okay, so before going to this, let us see the previous formula that we had. So before this, we were using this formula. So what was the formula? The formula was take the xt, multiply with the wxh. So current input, apply fully connected over that. Past state, apply fully connected over that. Add the bias, apply 10h, get the current state. Now in this case, when I'm involving the image, there should be involvement of the image also. Okay, so this part is coming from the above, this above. So we have, again, we'll be having xt, that is your input, and apply the fully connected over that. This is about the hidden state. Apply fully connected over the past past states, old state. And now there would be involvement of one more part, that is this. And what is this? Here we are adding one more fully connected layer, that is WIH. And this WIH is getting multiplied with input vector and that input vector is coming from here, and this input vector is having the feature of this image. Okay, so now what we are doing here, in totality we are adding the feature of the image, adding the feature of the input, adding the feature of the past state, adding the bias, and then this like applying the nonlinearity function and getting the new state. Okay. So for getting the new state, now we are also involving the image feature, and that's the difference between the previous basic RNN and this image based RNN, where we are also involving the image, because we have to give the description of the image. Okay, so this is the new equation. Now this is the new part that has been added here. Okay, so with the help of this you generate the new state, and then the current state, and then with the help of the current state, now we are going to predict the next word. Okay, so we started from this start token, start word, and now we have to predict the next word every time. Okay, so start, then you did it, and then it's giving you new next word as a man. Okay, now we do not know all those inputs, so what we do, since this man is the next word, now we take this next word as a current word for the next state, and again with the help of this man generate the next word. So you can see here, so man, then man will come as an input for generating the next state. So with the help of, again for man you will be having the vector, so x1, and with the help of x1, then s0, and then b. So every time you are going to involve these three things: hidden state, previous state, current input, and the feature of the image, and then again you will be generating h1, and then with the help of h1 again you will generate the y1 multiplying with why. So suppose this is giving in. Now in will be considered as a next input, and with the help of in you are going to generate this, generate next word. So in, again you have x2 for this, then we generate s2, then with the help of s2 we generate the y2, and y2 is your output, and that is your straw. It's like mapping of that. So in this way, like we are going to generate all those words, and at the end, like since you have to end somewhere, so we have end token. Okay, so that is like end character. So when your end character comes, then you have to stop there. So just like starting, you have to start from start word. In the similar way, you will be having the end word also. So started from the start word. Now once your end word comes, then you have to stop. And now whatever you got, that is your that is the description. So you can see like man in straw hat. This we have got from this from this for this image. Okay, so they have done this experiment considering a lot of images and text, and then they have shown the result. Now you can see like these are the results. These are some of the example results. You can see like here we are giving this image, and we are getting this cat sitting on a suitcase on the floor. A cat is sitting on a tree branch. A dog is running in the grass with privy. Then a white teddy bear sitting in the grass. So two people walking on the beach with surfboard. So we are getting these all the output. Okay. So these are the positive side. Okay. Let's see some of the failure cases. Now these are the failure cases. So here you are giving this image, and your model is saying, hey, a woman is holding a cat in her hand. And why your model is failing? Because the color of here, you can say like this is matching with the cat color. So your model is getting confused with the cat, and that's why it's saying, hey, this woman is holding a cat in her hand. So this is the wrong result that you are getting. Again, if you see here, your model is saying, hey, a person holding a computer mouse on a desk. Now, why it is happening? Because you can see like that person is holding the this smartphone, but your model is saying your person is holding a computer mouse on a desk. Now, why your model is so again, I'm just telling you, failure case is very important thing. So you have to see like first thing, like you have to observe all those, you have to find all those failure cases, and then you have to also interpret why it is failing here. You have to give the justification, because your model is getting failed. There could be some reason, that's why it's getting failed. So in this case you can say, hey, it's getting failed because color is matching with the cat, and that's why it's getting failed. Even some structure is also matching here. Now in this case, why it is happening? This is very appropriate. There is no confusion here, but why your model is getting confused? The answer is the data set on which your model has been trained. In that data set, there is no smartphone. So that is again old data set. So that time smartphone was not there. Okay. And that's why your model is not able to understand the smartphone. And since you are showing that a smartphone, so it has to give some answer. So it's trying to like saying, hey, it's looking like a computer. So it might be the case that it could be your mouse, because you will be holding mouse doing something on the computer. And that's why it's getting confused. So again, I'll just tell you, like, your model is dependent on your data set. So if you have not shown something while training, and while testing, if you're showing something new, then your model may fail, because model has not seen that thing while training. So again, that's why all the challenges are there, because your model is fully data dependent. You can see here, it's saying that a woman standing on a beach holding a surfboard. Now here, again, your model is getting confused with this water, because here water is there, and then it's in some ways looking like a surfboard structure, and it's like face wise, trying to understand like this is a woman, and it's giving this answer. Why this is giving? Because most of the time you have shown this type of image, where people were just holding the surfboard, and now you're showing this totally different image. So it's not there in that, and that's why your model is getting confused, because it's trying to match with some of the training samples, and it's in some way it's getting matched with these type of images, and that's why it's giving you like woman is holding this standing on a beach holding a surfboard. Again, you can see here a man in a baseball uniform throwing a ball. Actually, this man is catching the ball, but giving you throwing a ball. So your model may fail multiple times, and that's why there is research. So that's why it's like this area is evolving area. So, and you know that whenever you will be you will be having challenges, then you will be working on that, and then you'll solving it. So these are the challenges. So whenever you are doing something, you will be having a lot of failure cases. Then how to deal with those failure cases? How to solve it? So those are the research questions. And then people try to do it. People try to come up with new idea, try to come up with new algorithm which can give you better or robust result. So one thing is like, you know that your model is dependent on the data set. So whatever you are showing, it will do in that manner. But thing is like, sometimes even if something is there in the data set, still your model is getting confused. So how should we remove that confusion? So a lot of things are there. So either you can make data set in a proper manner so that it should be your model should be more robust, or it can handle uh, like different type of new images, or you can make the model in an appropriate manner, considering the same data set, so that your model would not be confused most of the time. Because sometimes even if the things are there, whatever new things you are getting, those are already there in the data set, but still your model is getting confused, like this part, because of this color. So you don't know what your model has learned, and that's why there's this problem, because there is no communication between you and your model. Your model is learning something, just seeing the data, and then you don't know what your model has learned, what function it is applying over the image. So that's why just observing the failure cases, you have to somehow interpret why it is getting failed and what should we do. And this is the research. We could again go for some, even we could be having even more challenging problem compared to previous. So in the previous case, we're just asking that like just your model was describing the image. Now in this case, we are going to ask the question from the image. Okay, and this paper came in ICCB 2015 and then CBPR 2016. And what they have done, they have just tried to ask the question from the image. Like this is the image, and I was asking when was the picture taken? I think during a wedding. Then who is under umbrella? 2 women. So just asking the question and your model is giving the answer. Or maybe asking multiple choice question, giving multiple choices and then saying, hey, tell me the true option. Tell me the right option. Okay. Then again, okay. So now the thing is like how this is being done. How to define the architectures for solving this problem. So in this case, again, you have two things. One is image and another one is text. But we have two inputs. One is image and one is text. In the case of image description, we have only one input. That was your image. And then we were predicting the words, predicting all the words. In this case, we have two inputs, image as well as sentence. So let's see how we do it. So again, whenever we have CNN, whenever we have image, we'll be using CNN. So use any CNN type of network. So suppose we are taking VGG net here. So take the image, process it through all those layers. And suppose you are getting this, at the end we are getting this 1024 dimensional vector. In the similar manner, you also have to process the sentence, the question, what has been asked. So suppose this is the question, how many horses are in this image? This is the image. So again, you process this using RNN, because whenever you have text, you use it RNN. You use RNN. So again, suppose one word is considered as a, like we are processing one word at a time. So how will be given to this? How many will be given to this? Horses will be given to this. So, and in this way, like you are generating the states. So these are the states, you are generating states. And at the end, suppose you once you process all the text here, now you got this vector. Again, you are considering same dimensional vector, what we have here. So suppose it is 1024. And now you are going to combine these two things. So one thing is the feature of the image. Another thing is the feature of the your sentence. So we had like this big sentence, like this sentence, and then we processed every text of this sentence and every word of this sentence, and then finally this is the final state. And you know that in the state you have the information of all the previous inputs. So if I just see like what is here, you can say, hey, in this state we have the information of this full sentence, and then you are combining it here, just doing the point-wise multiplication. So we are combining the feature of the image and feature of the states, feature of the this sentence, and then you are just processing it, and finally you are predicting. At the end, it's giving 2. So you're applying a lot of fully connected here, and finally it's giving you 2. So this problem can be seen as a this prediction, we can say regression problem, because you are just giving the number here. So how many horses are in the image and saying, hey, the image number, the horses are 2. Okay. So in this way, like you can make the model. So initially, like your model will give you wrong result. Then you have the actual value. You know, like what is the ground truth value, how many horses should be there in the image. That is known to you. That's your ground truth. Find the loss and go back, and then based on the gradient, you will be updating this part. You can also update this part, but in general, we train only this part, because for image we have a lot of good pre-trained model, so you can use it as it is. But this part you can train in a proper manner. Even sometimes, if you have sufficient amount of images, you can also train this part. So in the back, every part can be trained. All those weights can be updated. Okay. Now, even you can go make this problem more challenging. So I was here, like we were just asking the question from the image. Now go for asking multiple question from the image. Okay. So suppose you have given this image. It's called visual dialogue. Okay. So conversations about image. So just doing the conversation. So you are giving this image, and your model is saying, hey, a cat drinking water out of a coffee mug. So your model is giving the description. Now again, we have started to ask question. Hey, what color is the mug? So again, whatever output you are getting from the model, you are just asking the question from that output only. So just asking, hey, what is the color of the mug? And saying white and red. Then again, you are asking, are there any picture on it? Saying no, something is there. Can't tell what it is. Again, you're asking, is the mug and cat on a table? And your model is saying, hey, yes, there are. Yes, they are. Then you're asking, are there other items on the table? Saying, yes, magazine, book, toaster, and so it's even more challenging problem, because here this model also needs to like put, or it needs to store the past information. Because whatever you have asked, whatever answer you got, again you are asking question from that answer. So your model needs to understand, needs to understand the context. So that's why this is even more challenging. And nowadays you can see this using Chat GPT. So you can ask the question again and again, and your Chat GPT will able to. So what Chat GPT is doing? Chat GPT is also doing the similar type of stuff. So whenever you are asking something, and whatever its model is giving, it's storing that information in some history. So it's having the history where it's storing all those information, so that if next time if you're asking something from that history, then it will just search there, and it will try to, it will use that history along with the model, and then it will try to give you the answer. Okay, so I think I'll stop here. In the next class, we'll start with the vanilla RNN gradient flow. So we'll see what are the challenges there in the RNN, and then how to solve those challenges. So this we could see in the next class. So now I'll just stop here, and if any question, then I'll take it.
Sir, one practical class would be very helpful for us on this RNN and not on CNN but RNN.
Which class? You're talking about demo class?
Yes.
I think in short time it's very difficult to cover each and everything. So even if I give you one demo on CNN or fully connected, that will be also helpful, because again you'll be having the same trend. You'll be, even if you're going for RNN, the structure would be similar only. So let's see, if at the end, if we will be having some time, then I'll also try to cover this RNN in for the practical for the RNN. But it depends how much time we'll be having at the end. because we also need to cover the theory part. But I'll
Okay.
try my best.
Okay, sir.
I'll try my best. But before that, first, at least next week, we should be having this demo on fully connected, and also try
Sir,
to cover.
sir,
Yeah.
if you will share any code file with complete comments, then that would also be useful for us. We can go through that.
Okay, then I'll try to do it. I'll do it.
Okay, sir. Thank you.
Sir, I have one
Hmm.
question regarding the back propagation. For image, I do understand that we do give a ground truth stating that this image signifies this particular
Hmm.
thing. For example, this
Hmm.
uh,
Hmm.
slide that you are showing, that man in straw hat. But how
Hmm.
will it happen in text? Because first you started with small characters. So will
Hmm.
the back propagation happen in characters, or would it be a complete text? I am not able to understand that.
No, actually, the example that I've shown to you, that is based on character. But in general, even if you are dealing with the text, in that case also, like you'll be taking one word as a one in as a input. Okay, so instead of taking character, because if you go with the character now, it's very difficult to control it. So that's why we don't go with the character level or alphabet level. Okay, we generally go with the uh, this word level. So just like this. So we'll be having the man input. Then you are going to predict next word, next word. With the help of current word, you are going to predict the next word. Again, with the help of this, we are going to predict. So in this manner, like you will be having the similar approach even in the case of word this text also. So what was your question? Like you
No,
were.
what I am asking is that for word, as you said, okay, we do word, but would that be in a cumulative way? For example, the way you showed that if I want Y1, I would be taking reference from the previous H, that is H0. So if I go in backward propagation, what reference will it take reference, or it will just start back propagation as it was doing in connected, fully connected thing?
No, no. So whenever you are going back, you should be having loss now. So loss, you need to calculate the loss. So for loss, you should be having the prediction, and then you should be having the ground truth actual value, and then only you will be going to predict. Then only you will be going to calculate the loss. Let's take one example. Suppose you have to do the sentiment analysis. Like you have to say like what is the sentiment of the paragraph. Okay, so what you'll do, you'll divide your paragraph is having a lot of words, so you'll start processing one word at a time. So you have the paragraph, you start processing one word at a time and generating the state, because you know that using every word you can, like using one word you can generate one state. So every word will give you the state, and since in this case your goal is to do the sentiment of the full paragraph, so you are not going to predict the output at every state. That's not useful here. Okay, because you have to generate the output at the end, because it's just like whether positive, negative, or neutral, and that is like for the full paragraph. So again, what I'm telling you, like it depends on the problem statement what you are solving. So in every case, you are not going to predict the next word. It depends like which problem you are solving. So if you are solving sentiment analysis, then you are not going to get output at every state. Instead, what you'll do, when you process every word of this paragraph, then at the end, whatever state you have, you know that this state is having the information of every words which you have shown to the RNN. So just using this state, you can predict the output. So now this state would be given to the WHY, and that WHY will give you class either positive, negative, or neutral. But you also know in while training, you also know in advance that what is the class of this paragraph. So you know like what is the sentiment in that paragraph. So whatever your model is saying, you will be checking that with your ground truth, the actual. And then suppose your model is making mistake, it's saying wrong thing. then you will say, hey, you are making mistake. And then how to find that how much mistake your model is making? So for that you have loss function. So you compare with the actual, you compare your prediction with the actual, and that is the loss, and that loss should go back. And then it will go through every state, and at the end, go back means just finding the gradient, and you will go, reaching here, and then you will be updating the weight. So this is like, again, it's like when we have predicting the output at the end. But if you're predicting output at every state, like for every state, then suppose you process till this point, now you have to go back, just aggregate all the loss, and then with the help of that loss, you start going back. That means like you're finding the gradient, and then at the end, whatever gradient you got here, like the L of WXH, L of WHH, and del of WHY. These three things you need to calculate, and whatever you are getting at the end, now with the help of this, you update the WXH. With the help of this, you update the WHH, and with the help of this, you update the WHY. Now, did you get the?
Yeah. So this RNN can be twisted as we want. We means it can take the entire sentence or it can take fragments of sentence. So that depends upon the application. Got it.
Yes. Depends on the application. So it will take one more lecture to complete it, because I thought of completing few more slides, but then realized that no, I should stop here, because now we'll be having some mathematical structure there. So it's good that we'll be starting in a fresh mode, maybe in the next class. And because now again we have sufficient time, we can complete all those chapters what we had planned before. Okay, if there's no question, then I'll stop here.
Yes, sir.
If any quick, okay, thank you. I'll stop here.